Hello, I am Shashanka Venkataramanan from the Center for Research in Computer Vision at the University of Central Florida. My work entitled Attention Guided Anomaly Localization in Images is a joint work with Kuan-Chuan Peng, Rajat Vikram Singh, and my advisor Abhijit Mahalanobis. We address the problem of anomaly localization in images, in which, given an image, we first detect the image as normal or anomalous and then localize pixel-wise anomalies within them. Anomaly localization has been widely applied in industrial inspection settings to segment defective product parts, in surveillance to locate intruders, in medical imaging to segment tumors in brain MRI, or glaucoma in retina images, etc. This task is challenging due to the small pixel coverage of the anomaly and lack of suitable anomalous data, since images with anomalies are rarely available in real-world scenarios. Existing state-of-the-art methods tackle this challenge using autoencoders and GAN-based approaches using thresholded pixel-wise difference between the input and reconstructed image to localize anomalies. However, these methods compute class-specific thresholds using anomalous chaining images, which can be unavailable in real-world scenarios. Furthermore, some methods localize only a single type of anomaly, while other methods perform patch-based anomaly localization instead of pixel-wise localization, which leads to suboptimal performance. To overcome these challenges, we propose CAVGA, which is a convolutional adversarial variational autoencoder with supervision on attention maps to localize anomalies. We are motivated from the findings in GAIN that attention-based supervision can alleviate the need of using large amounts of training data. Unlike prior works, CAVGA localizes anomalies without using any anomalous training data, is capable of localizing multiple types of anomalies, and also localizes pixel-wise anomalies. We now discuss the main idea of our work. Given only normal training images, we encourage the attention map to focus on all the normal regions of the images, while minimizing the attention map corresponding to the anomalous regions. During testing, once the image is detected as anomalous, the anomalous attention map localizes the anomaly in the image. The contributions in our work are that we propose a convolutional adversarial variational autoencoder with guided attention for anomaly detection and localization. In the unsupervised setting, we propose the attention expansion loss, and in the weakly supervised setting, we propose the complementary guided attention loss. CAVGA outperforms state-of-the-art anomaly detection and localization methods on 6 benchmark datasets in various domains. Variational autoencoders have been widely used for anomaly detection. As compared to prior works, which use a flattened latent variable, we employ a convolutional variational autoencoder with a convolutional latent variable to preserve the spatial relation between the input and latent variable. Our convolutional VAE is trained using reconstruction loss and KL divergence loss. Since vanilla VAE generates blurry reconstruction, we use a discriminator to generate sharper reconstruction using adversarial learning, which also encodes better features in the latent variable. We now discuss CAVGA in the unsupervised setting. The main contribution of our work involves using supervision on attention maps to spatially localize the anomaly in the image. Given the lack of prior knowledge about the anomaly, in general, humans need to look at the entire image to identify anomalous regions. We use this notion to learn the feature representation of the entire normal image by proposing an attention expansion loss, where we encourage the network to generate an attention map covering all the normal regions. We use the feature representation of the latent variable z to compute the attention map using GradCam. Intuitively, the attention map obtained from the feature map focuses on the regions of the image based on the activations of neurons and its respective importance. The attention expansion loss is used as additional supervision on the network, such that the trained network generates an attention map that covers all the normal regions in the image. Hence, in the unsupervised setting, we form our final objective function, L final, as the weighted combination of reconstruction, KL divergence, adversarial, and attention expansion losses. We explored the possibility of using few anomalous training images to improve the performance of anomaly localization in the weakly supervised setting. Since annotating segmentation training data can be laborious, in the case when the annotator provides few anomalous training images without ground truth segmented anomalous regions, we extend CAVGA to a weakly supervised setting. We modify CAVGA-U by introducing a binary classifier C at the output of Z as shown, and train the classifier using binary cross entropy loss, LBCE. Given an image X and its ground truth label Y, we define P as the prediction of the classifier, where CA and CN are anomalous and normal classes respectively. We use GradCam to compute the attention map for the anomalous class and the attention map for the normal class on the normal image. Using the complementary guided attention loss, we minimize the areas covered by the anomalous attention and simultaneously enforce the normal attention to cover the entire normal image. Since the attention map is computed by backpropagating the gradients from P, any incorrect prediction would generate an undesired attention map. This would lead to the network learning to focus on erroneous regions of the image during training. Thus, we compute the complementary guided attention loss only for the normal images correctly predicted by the classifier, that is, if P is equal to Y is equal to Cn. We represent the complementary guided attention loss as the following equation, which is satisfied only for the normal images correctly predicted by the classifier. It expands the normal attention map and minimizes the anomalous attention map on the normal image. Hence, in the weakly supervised setting, we form our final objective function as the weighted combination of reconstruction, KL divergence, adversarial, classification, and complementary guided attention losses. We evaluate CAVGA on the MVTec Anomaly Detection dataset, ShanghaiTech Campus dataset, LAG dataset, MNIST, CFAR10, and Fashion-MNIST dataset. Since the ShanghaiTech Campus dataset consists of videos and we address image-based anomaly localization, we take every fifth frame of the video to create a modified ShanghaiTech Campus dataset. For all these datasets in the unsupervised setting, we do not use any anomalous images during training, while in the weakly supervised setting, we use only 2% of the anomalous training images. Examples of images from these datasets are shown here. We use the convolution layers of ResNet 18 as our encoder, pre-trained from ImageNet and fine-tuned on each category or scene individually. We use a residual decoder with a convolution layer interleaved between two upsampling layers. The skip connection is added from the output of the upsampling layer to the output of the convolution layer. We use the discriminator of DCGAN, pre-trained on Celebi dataset and fine-tuned on our data as our discriminator, and term this network as CAVGAR. For fair comparison with the baseline approaches in terms of network architecture, we use the discriminator and generator of DCGAN pre-trained on Celebi dataset as our encoder and decoder respectively. We keep the same discriminator as discussed previously and term this network as CAVGAD. We observe that CAVGAU outperforms all the baseline methods on the MVTec Anomaly Detection dataset with a higher IOU. Furthermore, we also observe that using few anomalous training examples in CAVGAW improves the performance of anomaly localization as compared to CAVGAU. We observe a similar performance trend on the modified ShanghaiTech Campus dataset and also on localizing glaucoma in retina images in the LAG dataset. CAVGA outperforms all baseline methods in terms of mean IOU and mean area under ROC curve denoted as AUROC on the MVTec Anomaly Detection dataset, modified ShanghaiTech Campus dataset, and also on the LAG dataset in terms of IOU. CAVGA also outperforms state-of-the-art anomaly detection methods on 3 academic benchmark datasets, MNIST, CFAR10, and Fashion-MNIST, with an improvement ranging from 0.1 to 2.5%, 3 to 31%, and 2 to 24% respectively. To test the effectiveness of using attention expansion loss in the unsupervised setting, we train CAVGA without the attention expansion loss. We observe that the attention expansion loss improves the localization in the unsupervised setting. Similarly, in the weakly supervised setting, we train CAVGA without the complementary guided attention loss and observe that the complementary guided attention loss improves the IOU. In summary, we propose an end-to-end convolutional adversarial variation autoencoder using guided attention, which is a novel use of this technique for anomaly localization. Applicable to different network architectures, our attention expansion loss and complementary guided attention loss improves the performance of anomaly localization in the unsupervised setting and with only 2% extra anomalous images for training in the weakly supervised setting. CAVGA outperforms state-of-the-art anomaly localization and anomaly detection methods on 3 real-world and 3 academic benchmark datasets. Please read our paper available at this QR code and join us during our live Q&A session. Thank you for your time.